Welcome to the last lecture for Chemistry 30 Prep. We're going to talk about indicators and titration curves. In your textbook it's 317 to 322. In this lecture, by the end of it, you will be able to describe the process of performing a titration, identify the equivalents and endpoints of a titration, and describe the shape of a titration curve for titrations involving strong acids and strong bases. So here's just a brief description of how to do a titration. The easiest way to know how to do it is to actually do one, but being as this is an online course, it's not always possible. So the first step is the sample being analyzed. So our sample solution is going to be measured and put into an Erlenmeyer flask. To it, we're going to add an indicator, and what this does is it's going to let us know when the reaction's over. So we're going to talk about indicators as well, and say exactly what they're used for. After we take an initial volume reading from the burette, we start adding titrant. So we fill our burette with titrant, we take an initial reading from our burette, and then we slowly start to add it to our sample flask while we swirl it. And the swirling is just to make sure our acid and base, or that our titrant and our sample are mixing completely. The endpoint of a titration occurs when there's a color change. So it's going to start off usually clear. We're going to add an indicator to it, which might be colored, it might be not. We're going to start adding our titrant, and at some point a color change is going to happen. When the color change happens, we have seen the endpoint, which is going to be related to something called the equivalence point. When we read a burette, we read going down. And so on a burette, there are lines that go all the way around the burette at every milliliter. So here, this would be, the top would be up this way, and the bottom of our burette would be this way. And so we read going down. So this is 2 milliliters at the thick line. This next line would be read as 2.10, 2.20, 2.30, 2.40, so 2.50 would be this one, 2.50, 2.60 would be this line here. And so when we read our volume, you can kind of see in this picture there's a meniscus in the water. We look for the bottom of the meniscus. It looks like it's about here. So we'd say that the volume used, or at this level here, would be 2.5, and it looks like it's about 7-ish or so. So 2.57 milliliters is how much has been used from the top of the burette. So as you can see, burettes are very, very accurate. You can get to the 100th of a milliliter, which is really, really accurate. So again, the purpose of a titration is to find the concentration of something when our titrant and our sample are at stoichiometric amounts, or when they're equivalent. We've reached something called the equivalence point. To find this point, because most acids and bases are clear and colorless, and because most of their products are aqueous in solution, we can't actually see when the reaction is over. So what we're going to do is we're going to add an indicator, and an indicator is a chemical that changes color when it undergoes chemical reaction. So it's one color when it's in one shape, and another color after it's reacted with something else. When we see this color change, it's the endpoint. So there's 2 points. They're almost the same but a little bit different. Equivalence point refers to our reactants. Being in equal amounts. So there's no excess reagents, everything's been used up entirely. Oops. And so they're at equivalence. The endpoint is only about a color change of an indicator. So it's a color change of your indicator, and the 2 points are usually about 0.05 milliliters apart. So they aren't quite the same, but they're pretty close. So for a strong acid, strong base, the equivalence point can be determined by using pH. We know that acids form hydronium ions in solution, and strong bases form hydroxide ions. So for any acid or base, the basic reaction that we're looking at is the hydronium ion from the acid reacting with the hydroxide ion from the base. When they react, we get two water molecules. The pH of our two solutions before are going to be very different. The acid is going to be pH below 7. The base is going to be pH above 7. But at equivalence, when both of them are completely reacted, there's nothing left over of either, we're going to have a pH of 7, because the only thing that's going to be in our flask is water. So for acids and bases, the indicators we can use are the ones that indicate a change in pH. We can have something that's a certain color at low pHs, it's going to change to a different color at higher pHs, and therefore we can see when we've passed our equivalence point. So for simple acid-base titrations, our indicator detects the point where the acid and base are mixed in exactly stoichiometric proportions to neutralize each other. In other words, there's no excess or limiting reagents. The indicator is going to change color. It's called the endpoint. And in an ideal world, that happen at exactly the same time, but in reality, they happen a little bit separate. And note that not all acid and base titrations result in a pH of 7, but the ones for Chem 30 Prep do. Once we get into Chem 30, then we're going to find out that, well, not all of them reach a pH of 7 at the equivalence point, but for us they will, because we're always going to react strong acids with strong bases. Okay, so indicators. Acid-base indicators change colors. They're going to be one color in acidic solutions and another color in basic solutions. And the way they work is they're all monoprotic acids that are molecular when they're in their acid solutions. So they're going to be in a molecular compound as in an acid solution. They're going to ionize in basic solutions. And so an example would be something like, for methyl orange exists as a compound when it's in acid solution. So the hydrogens are going to be attached to some great big anion that we don't know the formula for, but that's okay. We just leave it as MO, which stands for methyl orange. In between pHs of 3.2 and 4.4, it's going to change color. It's going to go from red to the yellow. So between pHs of 3.2 and 4.4, it's going to be orangey in color. For bromothiamyl blue, it starts off yellow. In acid solutions, it ends up going from yellow to blue, so it's going to pass through a green phase on its way to blue, and it's going to be green between the 6.6 and 7.6. For phenolphthalein, it's in its more acidic form. It's colorless. At a pH of 8.2, it starts changing color. It's going to go through a light pink phase to a dark pink phase at a pH of about 10. So those are our colors. When we look at titration curves, now what titration curves do is they compare pH to the volume of titrant added. And now if we take a look at most acid-base reactions, if we have a sample of base and we're titrating it with an acid, our bases are all just hydroxide ions, and our ion symbol should be there, being titrated with hydronium ions. So for all acid-base reactions, we're getting to a product of water, and we know that the pH at equivalence would be 7. So here's what our titration curve would look like. And what we're doing, oops, my attempt at drawing a straight line, we'll try again. Okay, so what we're doing is, here's our burette, Then here's our Erlenmeyer flask. And we're measuring the pH in the Erlenmeyer flask as we add titrant to it. And so at the beginning, before we add anything, the pH is going to be up at 14. As we start adding acid to our solution, the pH is going to start to drop. And it turns out that it only drops slowly at the beginning. So this right here, the point where it's dropping slowly, this is called the buffer region. And so for a long time, the pH isn't going to change very much. But all of a sudden, as we start getting almost equal amounts of acid and base, we're going to reach this point on our titration curve where the pH changes rapidly. And so we get this rapid drop in pH, and then it'll go to a bottom. Here, from this point on, there's more acid in the flask than base. So from this point on, the acids would be in excess. In the middle of this big drop is going to be our equivalence point. For strong acids and strong bases, the equivalence point happens at a pH of 7. The equivalence point would be 25 milliliters for this particular reaction. And notice it's a hypothetical reaction, but the equivalence point is actually the volume of acid added. And this is cubic centimeters. It's the same as a milliliter. 1 cubic centimeter is the same size as 1 milliliter. If we reverse it, we end up with the same idea. So the same equivalence point is reached if the base is added to the acid. The only difference is the shape of our curve. If we're adding base to acid, then what we're saying is in our Erlenmeyer flask we have acid, and to it we're adding base. So here we have the acid, here we have the base, and we're adding base to the acid. So at the beginning, here's where we're measuring pH down here. Before we add any base, the pH of that solution is going to be really, really low because it's a strong acid. As we start adding base, the pH changes slowly. This is our buffer region. And then at some point, it's going to change rapidly. At the middle of that change is going to be our equivalence point. It's going to happen at a pH of 7. And again, the volume, in this case, is showing it to be 25 milliliters. So when we're choosing an indicator for strong acids, strong bases, we can see that for this region of our graph, the volume of base being added is very, very minimal. If you look down here, if we just sort of measure it down here and this one up here, so the range of volume is maybe 1 milliliter or less. What this means is we can choose any indicator that goes through a color change between a pH of about 3 and a pH of about 10 or 11. We'll say 10. Any indicator that undergoes its color change between a pH of 3 and 10 is going to change color quickly enough and soon enough so that we can find our equivalence point. So here's a summary. The graph on the left shows a pH curve obtained when we mix the base added to the acid. The curve on the right is the opposite. And so we said anything that changes color between about a pH of 3 and 10 is suitable for strong acid-base titration. So any of these indicators could be used when we're doing a strong acid, strong base titration to make our endpoint be relatively close to our equivalence point. And that's about it. So that's the last lecture for Chem 30 Prep. your Unit 4 problems or supplementary problems on page 753 to 755 in your textbook. Remember, the answers are in there as well. And good luck on the unit exam. Once you're done the unit exam, you can let me know about doing the final. Thank you.